Greetings and salutations, everybody. This is Jacob. Okay, so how the heck do we go about skinning this cat? Smoke came out of my ears trying to solve this problem, you say. Yeah, I thought I saw smoke the other day on the horizon. That was from you, wasn't it? Well, if it makes you feel any better, my friend, this problem made smoke come out of my ears as well. But rest assured, this problem is solvable. I'll walk you through this solution like there's no tomorrow. Oh, yes. So as the problem states, some dude or dudette is trying to get from point A to point B in the shortest time possible. His, let's just call him a he for now, speed when going through this region before getting to the bank of the river is 7 kilometers per hour. Let's call it a sandy beach. His swimming speed is 4 kilometers per hour. And when he gets to the other side, his speed increases to 9 kilometers per hour. So we're asked to find the minimum travel time. So we're going to have to formulate mathematically the time it takes for Jeff, we'll give him a name, to reach his destination. This is a variant of a problem I made a video of a few months ago, by the way, where some dude was running on a shore of a beach. Then he swam to a nearby island. Only this time there's one more speed to contend with. So naturally, there's going to be one more variable involved in this problem. So our desired function will be a function of two variables, my friends. Oh yes. We're taking it up a notch. Let's call this distance here x and this distance here y. So these two distances are going to be our variable. Oh yes. So y includes x, as you see here. And you'll see why we do this in a little bit. So the distance Jeff traverses from A to B is square root of x squared plus 7 squared, since 7 squared is the shortest distance between Jeff and the bank of the river from our initial conditions. And the time it takes him to get there is d over his speed on the sandy beach, which is square root of x squared plus 49 over 7. Okay, moving on to the water leg of Jeff's journey through the wilderness. So the distance Jeff swims from point B to C from the Pythagorean theorem, square root of y minus x squared plus 5 squared, since this distance here is y minus x, and the width of the river is 5 kilometers from our initial conditions. Since the swimming time is the distance he traverses in the water over his swimming speed, so now we have square root of y minus x squared plus 25 over 4. 2 down, 1 to go. Since this total distance here is 14 kilometers, and the remaining distance between Jeff and the finish line is 14 minus y, and this running time is 14 minus y over 9. So putting all this together, the total time it takes Jeff to get from point A to point D is given by this function here, function of x and y. So what do we do now, you ask? How do we minimize a function of two variables? Do you recall what a partial derivative is from your Calc 3 class? You've taken one? If not, no worries. I got you covered, my friends. Partial derivative is a derivative with respect to one of the variables of the multivariable function. The partial derivative of this function here with respect to x is you treat x as the variable, and the other variable you treat it as a constant. This is the notation of a partial derivative with respect to x, and this is the one with respect to y. So using the chain rule and the product rule, we have t of x equals x over 7 times square root of x squared plus 49 minus y minus x over 4 times the square root of y minus x squared plus 25. And t of y is y minus x over 4 times square root of y minus x squared plus 25 minus 1 over 9. So what do we do with these partial derivatives? You do the same thing you do when you have a function of one variable. You equate both of these partial derivatives to 0. And so we end up with a system of two equations which we have to solve. This seems to be a common theme among the latest videos, by the way, my friends. I don't know if this is a coincidence or not. I love systems of equations. If you haven't picked up on it already, it could be a coincidence. But anyway, I digress. So what do we do now? We just solve for x or y in one of the equations and substitute the other in the other one, right? Plug and chug? Nope. Take a look at the second equation. How many variables do you see there? 2? Nope, not 2, just 1. That variable is y minus x. Oh yes, not x and y. So there's one variable in equation 2, y minus x, and two variables in equation 1, x and y minus x, not x and y. So we solve for y minus x in the second equation, and we substitute that in the first equation, since y isn't isolated in the first equation, so we can substitute it in the first equation. I talked about this variable combining technique in the snowplow video, by the way. There we had three variables and two equations, and we had to combine two variables to reduce the number of variables to 2. Here it's a bit different. We have two variables and two equations. We substitute y for another, y minus x, because this way the system is easier to solve. Because if you try to solve for y or x in the second equation, then you're going to end up with a quadratic formula, which you have to substitute in the first equation, and it just becomes a hot mess very quickly. So this is a more elegant way of doing things, my friends. Here we're combining two variables to make our life easier. Ooh, yes. Okay, so we solve for y minus x in the second equation, and we end up with y minus x equals 2.484 kilometers. And we substitute that into our first equation. We solve for x, and we end up with x equals 8.632 kilometers. And we solve for y in our first result, and we get y equals 11.11 kilometers. Now that we got our desired x and y distances, we substitute these values in our time function, and we end up with t minimal approximately 3.3 hours. Let's just quickly verify that this is indeed the relative minimum of this function. We'll apply the second partials test. We calculate this quantity here, d equals f of xx ab times fyy ab minus fxy ab squared. And if d is above 0 and f of xx ab is above 0, then f of a and b is a relative minimum, which is the case here. So this is indeed our minimum. So that's all she wrote, my friends. That's our answer. Oh yes, 3.3 hours. Intuitive answer or out of left field? You be the judge. To me, it's the former. Oh yes. So that was an interesting calculus puzzle, wouldn't you agree? I wanted to do something with multivariable functions, even though multivariable calculus isn't really my forte, so to speak. But I'm really fond of partial differential equations, which is quite odd. But don't you worry, we'll be back to single variable calculus in no time. And I'll do something with infinite series at some point, and limits, of course. The sky's the limit, pun not intended. I really do love puzzles that are physically motivated, not just calc puzzles, but puzzles in general. You've probably picked up on this by now. I don't like, for example, pulling out a random equation or expression out of a clear blue sky and asking you to solve it, like a math Olympiad question style. That's not really my style, my friends. I suck at those types of problems anyway, so there's that too. I gotta focus on my strengths and not my weaknesses, as they say. If there's an equation that's demanded of you to solve, then you can bet your bottom dollar that it's gonna be physically motivated on this channel, either through a physical situation or a word problem. When I say physically motivated, I don't necessarily mean a physics or a geometry problem. It can be any word problem in general. So long story short, word problems are the currency of this channel. Oh yes, they're the lifeblood of this corner of YouTube. We solve problems here on this channel, not exercises. I have to have a puzzle-like character. So that's pretty much it. Smash those buttons like there's no tomorrow. Shoot a puzzle and category suggestion my way. And I'll see you guys in the next video. Bye-bye.